Today I want to discuss some cryptography algorithms. Again, I am not a specialist in cryptography. I am even not a real mathematician, so it's just some basics just to show you how to use the algorithm we discussed in the previous lecture. So in the previous lecture we discussed some number theory algorithms and a lot of in modern cryptography based on these number theory algorithms. So today I just wanted to show how to use all this number theory to build modern ciphers. Go. So what is cryptography? How to use cryptography? No, basically what happens? There are two persons, let's see, A and B. They usually referred as Alice and Bob, but you can pick other names. You can say you have Angela and Boris. Why not? So you have two persons, A and B, and they are exchanging some messages. So they have some messenger or something. So they want to send each other some text messages or some files, some cute pictures of some cats, anything. So they have just common conversation, right? So I send messages here and I send messages here. And if they close to each other, they can just exchange messages physically, right? But if they are using some global network like internet, they send their message using this global network. So what happens when you send message in the internet? So it's not like you send the message directly to your partner. You send the message to the network, and inside this network, so there are multiple nodes. Yeah. So when you send the message from here, it passes many internal nodes of this network. And in these internal nodes, some other people can actually read your messages, if you're not careful enough. So let's say in this network, there is some, it's called attacker, it doesn't matter. So some another person, M from Mr. Putin, yeah? And he wants to read your messages. Yeah. Again, it's quite common situation, so it really happens. So the network are pretty open. So if you don't use any cryptography, then some people in your network can actually read your messages. Actually, when I was young, we had fun like this. So like 20 years ago, all these cryptography protocols were not that popular. So everybody uses just pure HTTP protocol. HTTP protocol is basically plain text protocol. So you just send your message in plain text. And if you just scan the packets inside your local network, you can learn many interesting about your neighbors. It's actually happening, yeah. So if you don't use any cryptography, then you can actually think that everybody can see your messages. Now, what to do? How to prevent any other person to read your messages? You should encrypt them. So you can use some cipher to encrypt your messages so that no one except your partner can read your messages. No, I'm not a real hacker, yeah. No. It's only for fun. No. So, for example, what can they do? The easiest cipher works like this. Let's say they have some message. So they have some message M. Let's put it from here. Let's say one direction. So I have a message M, and I want to transfer this message from A to B, so that M doesn't know this message. What I can do? Let's see. If this M, what is M? M is basically a sequence of bits. So let's say M is a sequence of n bits, like zeros and ones. What if A and B both know some secret key? So they both know some secret key of length m. So they both have this key. And the length of this key is the same as the length of the message. So the length of this key is n. So somehow both A and B find the same sequence of n bits, and they know this sequence and no other know this, and M doesn't know this sequence. Yeah. So what you can do? You can send message like this. You can calculate XOR of this message with your key. So you can calculate M prime as M, let's say XOR key, like bitwise XOR. Then send this M prime through this open network, and then B receive this M prime. He simply calculate M as M prime XOR K and get this message M. Yeah. Very simple cipher. So here's how you encrypt the message. Here's how you decrypt the message. What happens? What M sees? So if you are the person M, if you want to actually read this message from this open network, M knows only this XOR sound. So this is the only thing which is visible to this M. Yeah. So what can he get from this information? No, basically nothing. So if K is some random sequence of bits, then if you XOR any sequence with random sequence, you get a random sequence of bits. So this number M XOR K is some random sequence of bits. No, basically any bit can be 0 or 1 with equal probability, right? So if this key is some random sequence of bits, then this number is also some random sequence of bits. So M doesn't get any information from this sequence. Yeah. So M receives some sequence of n random bits. He doesn't know anything about this message M. That's all. Very simple cipher. It's actually working. You can do it like this. There are two problems. Problem number one. A and B somehow should get this shared key. So somehow this A and B should get the same key before they start the conversation. If they can meet in physical world, so if you just meet in some secret place and exchange the key, or just use some secret protocol to exchange the key, and so on. So if they can exchange the key without using this global network, just use another network which is secure to exchange the key. That's fine. But usually it's not the case. Usually when then there are two persons in different parts of the world, they cannot just meet in the same point and exchange the keys. So that's one problem. Another problem is that this key is only for single use. So you only can use this key once, because if you try to use it multiple times, so if you calculate, let's say M1 prime as M1 XOR K, and then M2 prime as M2 XOR K, and send these two sequences using this open network, then M actually can get some information. So this malware, he receives these two sequences, and they are not random sequences. They correlate to each other, right? So just knowing these two sequences, he can get some information about your messages. For example, he can XOR M1 prime and M2 prime and get XOR of M1 and M2. That's some information about your messages. So if you just calculate M1 prime and M2 prime, you will get M1 XOR M2. That's not your messages, but it's something. Yeah. So you get some information about your messages. That's bad. If you get much information about your messages, you can actually find the contents of your messages. Yeah. Okay. No, for example, you can calculate frequencies of different characters and then match them to the frequencies of different characters in your messages and so on. So there are some methods to retrieve some information from this data. So if you receive at least some data about your messages, there are some other methods like analysis of frequencies and so on. So you can get some information later on. So it's bad. Now, so again, there are two problems. First problem, how to get the shared key, and second problem, that keys can only be used once. What to do if you want to send multiple messages? You can get multiple keys. Yeah? So if you want to send multiple messages, you can generate not single key but the big array of keys. Yeah. So you calculate keys K1, K2, and so on. K. What number we have? K. Let's see, big N. Yeah. So let's calculate the big number of keys. Share them between A and B. Now they can send the messages until they get so until you use all the keys, you can send the messages. Yeah? What's the problem? The problem is this set of keys is still some finite set of keys. So you can send the messages, but when you run out of keys, you can do anything. So this is still still not permanent solution, right? So it's some temporary solution. You can do it until you run out of keys. This problem actually happens. So I'm not sure when, but long time before, when spies use keys like this, they actually get problems like this. So they have some limited number of keys, and they use these keys to cipher the messages to the headquarters. Yeah? And then they run out of keys. They still need to send some messages, and they reuse the same keys over and over again, and they get caught because again this messages was read and they how it's called, I don't know. So some people who code spies, they actually can retrieve information from these encrypted messages just because they use the same key to. Yeah. Another solution is to have some infinite sequence. So let's say that A and B both have the same random generator. Yeah. So they have a random generator. So this sequence is actually infinite. And so if you have a random bits generator, you can generate infinite number of bits. The problem is that A and B need to have the same generator. Yeah. So you must give A and B exactly the same random generator, so they generate the same bits. No, there are some random generators, right? So usually in your computer you use some pseudo-random generators, right? So you use something like, no, usually how the pseudo-random generator works, it has some seed, and then you generate, each time you use this seed to generate the next seed using some simple formula. And then and so on, so you generate infinite list of something which is actually usually pretty random. The problem is that if you use generator, if your generator is not specifically built for cryptography, it may have some how it's called again, some flaws. Yeah. So if your generator is not built specifically for cryptography, then something like that will happen. So if you somehow, if M somehow gets some first bits of this sequence, and it may happen because, for example, you send some file. This file have some header, yeah. So this header is always the same. So if you know the header of the file, you can XOR and get the first bits of your key. And if you get enough bits of your random sequence, since your random sequence is not actually random, it's pseudo-random, yeah. So if you get enough bits in the prefix of this sequence, you can retrieve all other bits. So you can retrieve the seed of your pseudo-random generator, and when you have the seed of your generator, you can generate all other numbers. It actually could happen. So, but it is this problem is also solved, mostly solved So there are some specific generators built specifically for cryptography. So they doesn't have this problem. So they even if you get some bits in the prefix, you will not get the future bits. They're pretty complicated, but let's believe they are working. Another solution is to use some misselected. So there are other ciphers which actually work simpler than this, but there are some ciphers which is block ciphers. Yeah. So there are standard ciphers which uses kind of strange operations, but they work pretty good. So what's okay, it's hard to explain how to say if cipher is good or bad, but there are some good ciphers which works with the given key. So if A and B share the same key, there are some good ciphers which can encrypt your data, and it is pretty secure. So they kind of shuffle the bits, they XOR them with something random. So in the end, you have no patterns in these bits and so on. So this problem is actually pretty much solvable. It's not that complicated, but there are some different ciphers for this. But again, if A and B have the same shared key, then they can actually exchange the message using some shared key cipher. There are a lot of them, and they are pretty good. They are good, and they actually what's actually even more important, they are pretty fast. So you can use them basically to cipher anything. You can use them to encrypt your file system. Just in modern computers, the whole file system is encrypted, and you use some fast ciphers for this. And you can encrypt like all your network connections. So if you use VPN, for example, VPN is encrypted. Or if you just watch the videos on YouTube or on Twitch, so the whole YouTube stream is encrypted. Yeah. So you watch the video, this all this video stream is encrypted. So they are pretty fast, they are pretty good. So this problem is pretty much solvable. What about the next problem? So the only problem what's left actually is how to get this shared key. So if A and B manage to have the same key, the problem is pretty much solvable. The problem now is how to get this shared key for both A and B. Go. So to get this shared key K, we will use something which is called an open key encryption. Yeah. Yeah, it's called like. So what is an open key encryption? It works like this. You have not a single key, but you have a pair of keys. One key is public, another key is secret. Yeah? So you have key public and key secret. And you use one of the keys to encrypt your data and another key to decrypt your data. So you have basically two functions. You have M prime encrypt from M using this public key. And when you decrypt your data, you take this encrypted message and this secret key. Like this. So it's not symmetrical, yeah? So to encrypt the message, you use only this public key, but to decrypt the message, you need to know this secret key. Now, what happens if you have a situation like this? If you have a situation like this, you can exchange messages. For example, let's say A want to say message to B. So I want to say message M to Boris, and I don't want anyone else to see this message. So I contact Boris and tell him, Boris, I want to send you a message. Yeah. So Boris generates public and secret key. So it has public key and secret key. Yeah. So Boris generates pair of keys. Now he sends this public key back to Angela. So let's say K public. Yeah. Angela uses this public key to encrypt this message. So she calculates M prime as encrypt of M and public key. Now she sends this M prime here. Now Boris uses secret key to decrypt this message back. Yeah. So he calculates M as decrypt of M prime and key secret. That's basically how it works. So again, what do you know if you listen for the messages in this network? You have this M here. So what does he know? He knows the public key and he knows encrypted message. And this information is not enough to retrieve the message itself, yeah? Because to retrieve the message, you need to this decrypt. To decrypt the message, you need secret key. M doesn't know secret key. He knows only encrypted message and public key. That's not enough to decrypt the message. That's the whole idea of this protocol. Now, how to build protocol like this? To build protocol like this, you need something which is called, how it's called in English? Say one-directional function. So you need some function which is easy to calculate one way but hard to calculate other way. So let's say fx is easy to calculate, but in other way is hard. So to build this protocol, we need some function which is easy to calculate one way but hard to calculate other way. What does mean easy calculate and hard calculate? It actually means that you can calculate this function fast enough, and you cannot calculate this function fast enough to be to use it in practice. So this function can be calculated fast, and this calculation can be calculated fast enough to use it in practice, right? No. Ideally, you want this function be easy to calculate, and this function is not possible to calculate at all, but it's impossible, right? So if you can calculate function, you can always calculate the inverse function. You can just check all possible arguments of your function and find the argument which matches your. So again, what you want to do here, you want to find y such that f of y equals to x, right? So this is what inverse function means. And so if you can calculate function f, then you can just iterate over all possible values of y and check each value that the function equals to x. So it's always possible to calculate the inverse function. The idea is it is very hard to calculate function. So you need to spend a lot of time to calculate this function, and this time is so large that it is practically impossible to calculate this function. Yeah. For example, again, why the P and P problem is important here? Because if you can calculate a function in polynomial time, so this problem is in P, then calculating the inverse function is obviously in NP. So if you can calculate something in polynomial time, you can calculate the inverse function in polynomial time on non-deterministic Turing machine. Yeah. How do you can just guess number y in your non-deterministic program and then check that it is x. Yeah. So it's obviously is in NP. So what if p equals to NP? If p equals to NP, it means if we calculate any function in polynomial time, we can calculate the inverse function in polynomial time as well. So if p equals to NP, it's pretty hard to get a good one-directional function. So we pretty much hope that p is not equal to NP. No, even if it is equal, so even if p equals NP, polynomial time doesn't mean that it is fast enough in practice. So it's a good sign that we can find a fast program, but polynomial doesn't always mean the program is fast, right? So if this big polynomial, so its power of this polynomial is too big, they still may have problem to calculate the inverse fraction. Okay. You're too quiet, say something. Is it clear enough by now? So, what's next? Let's give some example of. Today we'll discuss two examples of one-directional function and build some cryptography schemes from this. We will build two cryptography protocols using two one-directional functions. First one-directional function, very simple, is multiplication. So if you have two prime numbers, then you can calculate m from, let's n by m. N as product of p and q. It's very simple one-directional function. So if you know two primes, you can multiply them very easily and get the number n. On the other hand, if you have number n, how can you get this p and q? No, you need to factorize this n. And like we discussed in the previous lecture, we cannot factorize numbers fast. So we can move from pair of p and q to this number n very fast. And we cannot go back. Yep. Second example is discrete logarithm. So second example is that you have, let's say you have some prime and you have some generator G. Remember what's a generator? We discussed it last lecture. So generator is basically a number, so if you take all powers of this number, you get all numbers from 1 to p minus 1. So let's take some integer x and calculate g in power of x. It's another example of one-directional function. So it's quite easy to calculate g in power of x if you know number x. So you just use this. Again, we discussed it last week. So you just use this binary multiplication to calculate g in power of x. But it's hard to go back. So if you know the number g in power of x, again, it's modulo everything modulo p. So if you know the number g in power of x modulo p, it's hard to get the number x from this information. So all these powers of g are binary exponentiation. Yes, good order. So it's pretty hard to get this number x from this number. That's what I mean. It's called discrete logarithm, and again, it's one of the problems we don't know how to solve in polynomial time. Okay, so there are two one-directional functions, and we will build two cryptography protocols using these functions. From this function, we'll use protocol which is called RSA. From this function, we'll build protocol which is called El Gamal. Go. Well, let's build RSA first. RSA. Well, let's go. So how to generate keys for RSA cipher? Let's generate two primes, P and Q. So you generate P and Q, big random primes. Random primes. Again, a week ago we discussed how to generate big random primes. You just pick random number, check if this number is prime. Now, let's calculate n as product of p and q. Now let's see how the Euler function of this n looks like. So what is phi of n? Again, phi of n is the number of integers from 1 to n minus 1 which are co-prime with n. So how many integers are co-prime with n if n is a product of two prime numbers? Again, it's quite easy to see actually that the number of these co-prime numbers is p minus 1 multiplied by q minus 1. Again, it's easy to see actually. You want to calculate number of integers co-prime with n. These are all integers except all integers divisible by p and all integers divisible by q. So you just calculate number of these integers and you get this formula. Now, what next? Let's take random number n, co-prime with phi of n. It's usually quite easy to pick any number. Yeah. Usually you can pick number 3 in this co-prime with phi of n. Sometimes it's not co-prime, you can pick 5. So there are many numbers co-prime with phi of n. So you just pick any of them. And now you calculate number d as E inverted modulo phi of n. How you calculate this number? You use the Euclid's algorithm from the previous lecture. So in the previous lecture we discussed how to divide in the field of modulus. So you just use this algorithm to calculate this number. Again, just remind you. So to calculate this number, you solve the Diophantine equation like this. So this dE equals 1 modulo phi of n. It means dE plus something phi of n equals to 1. So it's Diophantine equation. You solve the Diophantine equation using the Euclid's algorithm, and you get the number d. That's all. And now you just say that the public key is n and e, and secret key is n and d. That's all. It's the whole algorithm. Now, how to encrypt your data using this protocol? Let's say you want to encrypt the message, and let's say this message is a number from 1 to n minus 1, and m is co-prime with n. No, there are many co-prime numbers with n, so usually it's not a problem. So you can encrypt all possible messages. You can encrypt messages which are co-prime with n. It's not a big problem because almost all numbers are co-prime with n. So m has only 2 big prime factors, so it's pretty hard to pick number which is not co-prime with n. Now, how to encrypt? Encrypt. Second prime. Okay. So we'll encrypt data like this. We will calculate the number which is m power e modulo n. Yep. Again, we'll just use binary exponentiation to calculate this number. How to decrypt number? So to decrypt the number, decrypt m prime and k secret. We will just take this encrypted message, put it in power d modulo n, and it will be message. That's all. It's a whole protocol. Well, let's prove it's actually correct. Let's prove that if we encrypt message like this, we can decrypt it like this. No, let's see. So if we calculate m power e modulo n and then take it in power of d modulo n, then what happens? We have m in power ed, yeah? Modulo n. What is ed? ed is just one modulo phi of n. So we have m in power 1 plus something multiplied by phi of n. So it's m multiplied by m in power k phi of n. This thing is 1, so it's m. That's all. Now let's see. So why can you decrypt the message using just public key? If you have only public key, then to decrypt the message, you kind of need this number d, right? So to know this number d, you need to calculate e in power minus 1 modulo phi of n. To calculate e in power minus 1 modulo phi of n, you need to know phi of n. To know phi of n, you need to find the factorization of number n. And we don't know how to find factorization of number n. So again, to decrypt the message, you need number d. To get number d, you need phi of n. To get phi of n, you need factorization of n. If you don't know factorization of n, you cannot find number d. That's all. That's all. Now, let's move to the second algorithm. El Gamal. Check how it's show. Just like this. Okay. Let's talk about Diffie-Hellman first. Let's talk about Diffie-Hellman protocol. So, Diffie-Hellman protocol, very easy protocol. So, I have A and B. Yeah. And I want to find some shared key K. So I want this key to be the same for A and B. How can I get the same key for A and B? Easy scheme. So let's take some big prime number. And take a generator. We can actually use the same generator for everything. It's not a problem. So it generates, like we discussed last week, so it's sometimes we have problem to find the generator. So to find the generator, you need to factorize p minus 1. So you need to get the number p, which is prime, and such that p minus 1 is easy to factorize. So it's kind of. So let's say we have some number p and some number g. Yep. Now what can we do? So A, generate some random number x. And B, calculate some another random number. Let's say doesn't matter, from 1 to p minus 1. Now A calculates number g power x and send it to B. B calculates number g in power y and send it to A. Now, A knows number g in power of y and number x. So you can calculate g in power of y in power of x, which is g in power of xy. B can calculate number g in power of x, put it in his power of y, and calculate number g in power of xy. So we have the same number for A and B. We'll just say this number is a key. So we'll just call this number key. Now A and B have the same shared key. Very easy protocol, actually. What about the man in the middle? So if we have somebody here. So the man here, he sees this number g in power of x, g in power of y. It turns that it's pretty hard to get the number g in the power of xy from these two numbers. Yeah. So to get this number from these numbers, you need either to get x or y. Yeah. But it's hard to get number x from here, and it's hard to get number y from here. So you cannot get number g in power of xy from these two numbers. I have the special shared generator. We can use the same generator for everything, actually. So in this protocol, we don't use that the generator is random. We don't use that the number p is random. We use only that numbers x and y are random. So we basically can use the same numbers p and g for everything. We can generate it once and then use it for all possible conversations. I don't know how it's done in practice, actually. How is it done in practice? So this protocol is actually widely used. I believe they use some constant numbers p and g for everything. I'm not sure. Again, I'm not a cryptography specialist. I'm just... So I can know the parameters. Yes, even if M knows numbers p and g, it doesn't matter. Even if you know numbers p and g, you can get the discrete logarithm, and you can discrete logarithm. You can calculate this number. Do you stream some Raven every week? I stream lectures every week. Now, but again, this protocol is used when you need to have shared key. This is actually quite cool protocol. What's very cool about this protocol is that it's very fast. So we only need to send one message here and one message here, and we can do it simultaneously. So the delay is very small. So if A and B wants to, it's like a handshake, right? So they want to share this key, they just send one message here, and because it's actually one way to get these messages, they both have this shared key. So it's a very fast way to get a same shared key for two partners. Now, how to build encryption for this? You can actually build an encryption scheme for this. So you want to encrypt the message. Again, you have A and B. And you want to encrypt the message. Yeah. Message M, you want to send it here. So B, he generates number X. Random. And then calculate number, let's say, Y, which is G in power of X. Now, Y is a public key, X is a secret key. So he sends number Y to A. Now, how can A send this message using this public key? It's done like this. A generates some random number. Yeah, let's calculate some random number, let's say S. and then calculate two numbers. First number is, let's see, A is G power S. Yeah. And B is right. And B is M multiplied by Y in power of S. Yeah, like this. And then send both this number A and B to Bob. Yeah, good enough. Good enough. So again, the protocol works like this. I want to send message M to Bob. So Bob generates number X and number Y as G in power of X. Send number Y to S. So she receives number Y. She generates number S, just some random number, it's session key. So she generates some random number S, calculates G in power of S, calculate M multiplied by Y in power of S, and send both these numbers here. How can Bob retrieve this information about message from these numbers A and B? So first, let's see if we are malicious. So if we stand in the middle, what do we know? We know numbers Y, we know number A and B. Yeah. Basically, what do we know? We know G in power of X, we know G in power of S, and we know M multiplied by, so Y in power of S is basically G in the power of X multiplied by S. So the G multiplied by XS. So if you're in the middle, you can calculate these three numbers. How can you get number M from these three numbers? So again, to calculate number M, you need to know number G in power of XS. And you know G in power of X and G in power of S. From these two numbers, you cannot get number G in power of XS. So M cannot find any information about your message. What can do Bob? So Bob can get the message like this. So Bob knows the number A is G in power of S, and no number B is M multiplied by Y in power of S. So what is B? B is M multiplied by Y in power of S. What is Y in power of S? Again, Y is G in power of X. So it's M multiplied by G power XS, right? Now, Bob knows number X and he knows number G in power of S. So he can calculate G in power XS as A in power of X, right? So A G in power of S, I put it in power X, I will get number G in power of XS. And now I can just divide this number by this number. So I can get message M as B divided by this number. So I will put it A in power of X in power minus 1. And I will receive a message. That's all. That's how El Gamal scheme works. Nice. What's next? Let's talk about signatures. It's called El Gamal. Let me Google it. El Gamal encryption. This is called El Gamal encryption. And this is called Diffie-Hellman algorithm. How it's called? I'm not good about spelling names. Diffie-Hellman. Like this. Nice. Let's talk about signatures. Let's say, again, I want to send a message. let's remove. Let's say that Alice wants to send a message to Bob, and how can Bob actually check that this message comes from Alice? Oh, so you want to send again. You want to send a letter to somebody, and you want him to know that this letter is actually from you. So what you do in physical world, you put your signature on this lecture. On this letter, yeah. So you put your signature below this letter, and your partner can read your signature and check that it's actually your signature. So this letter comes from you. How can we do it in electronic world? So in electronic world, we can do the same thing actually. We can make something without electronic signature. So so again, let's say Alice has a message M. And she wants to sign this message somehow and send this signed message to Bob. How can Bob check that this message comes from Alice? Let's say Alice has some secret key. Yeah. Let's use, for example, RSA's key. So in RSA, Alice knows numbers A and E and D, and Bob knows only numbers A and E. So Alice knows this secret number D. So to show that this message is actually from Alice, Alice will prove Bob that she actually knows number D. So number D only known to Alice. So if he somehow proves Bob that she knows number D, it means that this is Alice, because she is the only one who knows number D. So how can I do it? We can do it like this. So you just calculate, you encrypt this number using your secret key. So you can calculate this number M prime using your secret key instead of public key. So you calculate M power D mod N. And then send both these numbers to Bob. So they send numbers M and M prime to Bob. Now Bob receives these two messages, plain text message and message encrypted with this secret key. So what can do Bob? He can check that this message was actually encrypted with the secret key of Alice. So Bob can calculate number M prime power E and check it is equals to M. So Bob checks that this encrypted message, if we decrypt it using this public key, we get the same message as M. It means that if someone gets this message M prime, he might know, he must know this number D, because you can get from number M to M prime only if you know this number D. And number D is a secret key, which is only, So Alice is the only person who knows this number D. So if he managed to get this number M prime, it means he knows, it means she knows this number D, and Alice is the only person who knows this number D. So that's how you prove that this actually message belongs to you. Good. What else could we discuss? Okay, there's another problem. Another problem is that Bob somehow to check that this message comes from Alice, Bob needs to know the public key of Alice. And how can he get the public key of Alice if he doesn't know about anything about Alice? Again, if there are just two persons and they want to communicate, they can somehow share this public key before. So again, you need somehow to get this key. So you need this public key of Alice somehow to transfer to B. If there is something in the middle, so what may happen? What may happen? You have this Alice here, you have this Bob here, and you have someone here. It's called man in the middle. So Alice wants to send message to Bob. He sends the message using some encrypted protocol, but he actually is communicating not with B, but with M. So they have very secure encrypted communication channel between N and M. And Mallory make the same encrypted connection here. So we have very strong encrypted connection here, very strong encrypted connection here. And Alice thinks that she's talking to Bob. Bob thinks that he's talking to Alice. But actually they both are talking with this Mallory. Yeah? So that's the problem. So if you don't know anything about your partner and you just send a message through this open network, you have actually if you don't know anything about your network, there is no way you can check that the person you're talking to is the person you're supposed to talk to. Is it clear enough? Is it clear enough what I want to say? Yeah. Again, imagine you have a public network, yeah, and you have some friend who lives far away, and you want to send some message to this friend. So you have all the encryption protocols and so on. So you try to make encrypted channel between you and him. But you basically cannot do it. Because if you try to send anything to the open network, inside this open network, there may be some man in the middle, like here. And he will communicate with you just mimicking your conversation with Bob. Yeah, is it clear what the problem is? Yeah. So you cannot do anything about it. So if you don't know anything about your network, you don't know anything about Bob, you cannot do anything about this. What you can do? You can share the public key before, but again, this problem. If you cannot, if your public network is the only way to communicate, you cannot do it. You can, for example, what can you do? You can publish your open key in some place which is only available to you. Like you can take your Codeforces account, if you're from Codeforces, and put this hash of your public key in your handle, or if not in handle, somewhere in your profile. So if you want to send your public key to Bob, you can send this public key, then calculate hash of this public key, and put it in some public place, like your Codeforce profile on something. So it's actually working. It's one of the ways to prove someone that you are you. But it's only working when you have few people and they know each other. So if you know the person, your person you're talking to has Codeforce account or something like that, or profile anywhere in Facebook, in anywhere. So if you know something about a person, that's fine. But if you have global network like internet again, and there are many actors in this network, like every website want to have a secure connection to all its clients. So you want to have secure connection between any two clients in your network, and without knowing any information about them. Yeah. Say something. I'm talking too much. Okay. So how the internet actually works? So imagine you want to connect to some code forces. Right? So let's say you are Alice, and you want to solve some problems on code forces. So you connect to site code forces. Yeah. So again, what's happening in the internet? You send some packets of information to the site code forces. The same, just send information. I am Alice. I want to solve the problems. Give me the problem statement. This site this is go to server in ITMO, server of code forces. It receives your messages. Like, okay, you want to solve the problems. Here is the statement of the problem. You receive this statement of the problem. Solve this problem. Put your solution in some packet. Send this packet to code forces. Code forces receives your packet, checks your solution, send your feedback again. So there's some communication between your code forces. You want to make sure that you're actually talking to code forces using some secure channel. So before you start the secure channel, you want to make sure that the server you're talking to is actually the server of code forces. So there is no somebody here in the middle who mimicking this code forces activity and just send you the same messages. So what's actually happening? Every site who uses HTTPS protocol. So HTTPS protocol is basically HTTP protocol with some security layer already. So every HTTPS site has something called certificate. So code forces site has some certificate which certifies that this site with this public key is actually code forces site. So in this certificate there is public key actually. Keep up. So a special certificate which says that this public key actually belongs to code forces. It's certified, so you can use this public key to talk with code forces site. So code forces, when you first access this site, he sends you this certificate. You check that this certificate is valid, that this public key actually belongs to code forces, and after this you actually can start your messaging with code forces because you know that this public key actually belongs to code forces. Yeah? Makes sense. So, how did the code forces get this certificate? No, there are special senders for this certificate. So, there are a few senders which actually, how do you know? There are some special senders which issues these certificates to different websites. So if you own some website, you can go to the certificate center and basically buy for small amount of money this certificate. It will actually certify that this site belongs to you, and you use this public key for your activity. Yeah. So how to check the certificate? So to check the certificate, you actually need to go to this certification center. Center. I don't know how it's called actually. So code forces send you his certificate. You go to certification center and check that your certificate is actually valid. So if your certificate is valid, you know this public key belongs to code forces, so you can continue to talk with code forces. How can you contact this certification center? To contact the certification center, again, you need some encrypted connection here. To have this encrypted connection, you need to know the public key of this certification center. So you have the same problem again. So it ends at some point. It ends like that. So some certification centers actually are installed right in your computer. So your computer actually knows some public keys of some certification centers. So you can check the certificates locally actually. So you don't need to connect the certification center using some secure channels. or you can open the secure channels using these public keys you have on your computer locally. Okay, you stop talking, so it's suspicious. Say something. I'm just telling the same thing over and over again. Okay. Finally, I want to talk about some interesting attacks on, for example, RSA systems. So, everything we discussed today is basically theory. In practice, everything is much more complicated. For example, let's talk about RSA cryptography. So, in RSA cryptography, we just proved that you don't know, you can find number D if you can factorize the number n. So if you know number E, you don't know how to find number D. In reality, everything is much more complicated. What you can do, for example, it's actually working. What you can do? So you send some message to server. Server receives your message. And to decrypt your message, server calculates m prime power d modulo n. So what's happening? You send the server some message, encrypted message, m prime. To decrypt your message, server needs to calculate this number. Now, how it's calculated? How to calculate my property? And again, like we discussed, so the power a b. So if we want to calculate a power b modulo n, how can we do it? So if, let's say, well, let's do it like this. Okay, let's do it recursorily, just for simplicity. If b equals 0, return 1. If b modulo 2 equals to 0, return over a square b, else. Okay, it's not that visual. Let's make it non-recursive. It will be a little bit more visual. So how to calculate a in power of b? Let's make c equal to 1. Now while b is greater than 0, you calculate. So if b is odd, then you calculate c multiplied by a modulo n, and then b is b divided by 2, and a is a square modulo n. Yeah. Return c. So that's how you calculate a in power of b. What's interesting about this code? In this code, interesting that the time you spend in this code is actually depends on the numbers you input. So number of operations in this code is actually different for different numbers. For example, in this if operation, it is only executed when we have when b is odd. So it's actually executed only when we have bit 1 in this in binary notation of b. Yeah. So again, the number of operations of this procedure depends on numbers a and b. So what happens in our case? In our case, number of operations of this procedure depends on number m prime and d. And we know number m prime. So if we can measure the time spent by server calculating this result, we can get some information about number d. So again, different numbers d will produce different number of operations of this code. So if you can measure very accurately the number of operations, and we can actually, so So we can measure time. We can measure time in computers very precisely. So if we can measure the time the server spent to calculate this number, we can get a lot of information about this number d. And by giving him different numbers m prime, so we just give them different numbers and say decrypt this, decrypt this, decrypt this, and measure time he spent to calculate this, to decrypt these numbers. And just by giving these times, we can get a lot of information about d, and we actually can retrieve the number d if we give enough encrypted messages. We had a problem about this in some of the regional ICPC contests a few years ago. It's actually working. You can do it. Alternatively, you can do the same thing just by calculating not the time complexity, but the power consumption. So if you have some small... So cryptography used everywhere. It's used, again, it's used in file systems, in networking. It's used even in your credit cards, you know. So if you have some credit card, it has some cryptography protocols inside it. So what you can do is to measure the power consumption of your reading device, which reads the information from your credit card. And using this power consumption, you can calculate again number of operations of this procedure. And when you get number of operations here, you can get information about number d. So again, even if in theory it's hard to get number d from number e, in practice there are a lot of other suspects you need to consider. So in practice there are usually all the attacks in practice are not connected to the theory behind this cryptography. So usually there are some much more simple ways to attack your cryptography protocols than just trying to solve this problem by itself. Do we have another? We want another thing or not? For example, okay, let's make one more example. For example, you want to, let's say, what may happen? Let's say you have some message and you want to send it to multiple friends. So you have different friends and you want to send them the same message. So you want the message and you have 3 friends. One friend has an 1 and E1, and 2 and E2, and 3 and E3. You want to send them all the same message. So what you do, you calculate your message power E1 mod N1. Yeah, not exactly. So in practice, it's often the case that to make the encryption faster, you use very small number e. It's actually widely used number 3. So if all these numbers equal to 3, let's say. Yeah. So again, number e is not very important in the cryptography in RSA cryptography. So important thing that we cannot take number d from number e. Even if number e is not random, if you just take number 3 as e, you still to get number d, you need to calculate the inverse number modulo phi of n. You don't know phi of n, but so you can calculate number d. So even if you know, even if number a is small, it's hard to get number d. But it is used in practice because it's easier to calculate. So to encrypt the number, we need to take the power of e. So if number e is small, it's faster to calculate m power a e. Yeah. So it's actually it's quite real. It's happening. So we want to encrypt our message for 3 friends. So we calculate m power 3 modulo n1. We calculate m power 3 modulo n2. M power 3 modulo n3. Do you see the problem? How can I get number m using these 3 numbers? Now let's take these numbers now. M1, M2, M3. So if you receive all these three numbers, how can you get number M? You see. No? Again, we discussed it last lecture. What do we have here? We have some number modulo n1, number modulo n2, and the same number modulo n3. We can use Chinese remainder theorem. So using Chinese remainder theorem, we can calculate number m3 modulo n1, m2, n3. And since m is smaller than all these numbers, then we actually calculate number mq. Now we take cubic root of this number and get the number m. So reality is a little bit more complicated than than theory. Again, for all these problems, there are a lot of practical solutions. So basically, what you do, what you need to do here is to add some randomness. So you don't want to encrypt the same data using different keys. So you want to add some random bits to your message, and then encrypt different messages. So it's called the salt of the message. So when you encrypt the message, you actually want to add some random bits in the beginning of your message, so it will be impossible to decode it using something like that. Is it enough? There was one more interesting. I forgot. I wanted to talk about something else, but I forgot. Okay, so I think it's actually enough. So it's just introduction to some cryptography. So again, it's not the cryptography course. It's just some examples of how to use these number theory algorithms in cryptography. So I think it's okay. I think it's enough today. Okay.